we're diving into a genuinely fascinating, kind of invisible world, the place where matter just transforms right before our eyes. We're looking at the absolute core of how the universe builds itself up from the most basic ingredients. I mean, think about the sheer diversity of stuff around us, from the water we drink, the air we're breathing, to the solid ground we're walking on. It literally all comes down to atoms interacting. In this explainer, we're going to focus in on chemical reactions, and more specifically, the incredible power of chemical combination. It's basically the fundamental mechanism of how simple substances join forces to create this massive, complex world we live in. But hey, before we get into exactly how these things combine, we really have to ask a foundational question. How do we actually know a chemical reaction has taken place? It's a huge thing to consider, right? Because atoms are way too small for us to see. They aren't exactly raising little flags to tell us, hey, we just broke our old bonds and formed new ones. So what are the clues? How do we actually spot the invisible, foundational mechanics of the physical world when they're happening right in front of us, whether that's in our kitchens, in a lab, or just out in nature? Okay, so the crucial point here is that we have to look for telltale physical signs. We're relying on our own senses to observe the macro-level effects of these micro-level changes. There are really four main clues we look for to figure out if a chemical reaction has gone down. First up, a change in state, like a solid suddenly producing a liquid or a gas out of nowhere. Second, a change in color. Third is the evolution of a gas. So think fizzing, bubbling, or smoke. And finally, a change in temperature, where the mixture suddenly gets noticeably hotter or colder to the touch. If you see one or more of these things happening, well, the fundamental identity of your substance has changed. You are literally witnessing a chemical reaction in real time. Let's make this super concrete. There's a real drama to chemistry sometimes, and a perfect example is burning a magnesium ribbon. If you take a clean piece of solid magnesium with some tongs and hold it to a flame, it almost instantly reacts with the oxygen in the air. And wow, the result is absolutely spectacular. It burns with this incredibly dazzling, bright white flame. Now think back to our checklist for a second. We've got a massive change in temperature because that flame is incredibly hot. We also have a change in state and color because that shiny, solid metal ribbon transforms entirely into a crumbly white powder that just falls away. And that white powder? That's a brand new substance called magnesium oxide. So, to actually understand what has happened to that magnesium, scientists use chemical equations. Now, I know the word equation can sometimes sound a bit intimidating, but honestly, let's lower that barrier right now. Just think of it as a super simple, straightforward recipe broken down into two sides. On the left-hand side, we have the reactants. These are your raw ingredients, the substances that are about to undergo a chemical change. Then we drop in an arrow pointing to the right, which basically just means yields or becomes. And on the right-hand side, we have the products. This is your final, newly formed substance. The golden rule here is the law of conservation of mass. Atoms don't just magically disappear or pop out of nowhere. The atoms of the reactants on the left are simply broken apart and rearranged into the completely new products on the right. Which brings us perfectly to the core mechanism we're exploring today, the combination reaction. The definition is beautifully simple, but it is profoundly important. A combination reaction is simply a reaction where a single product is formed from two or more reactants. You can kind of think of it as a chemical marriage. You've got two or sometimes more completely separate elements or compounds that join forces, bond together, and become one entirely new unified product. That burning magnesium we just looked at? Magnesium plus oxygen yielding magnesium oxide. Two reactants, one single product. It is literally the textbook definition of a combination reaction. Let's quickly look at a couple of famous examples that literally govern our world, just to really lock this concept in. First, think about burning coal. You've got solid carbon, represented by the C, combining with oxygen gas. Two reactants, and they combine to form a single product, carbon dioxide gas. Now let's scale that up to something even more fundamental to our very existence, the formation of water. Here, two molecules of hydrogen gas chemically combine with one molecule of oxygen gas. And what do they yield? Exactly one product, water. Two or more ingredients on the left, exactly one unified product on the right. Simple as that. Now obviously chemistry isn't just about shuffling letters around on a page, right? It's a highly energetic process. When these new chemical bonds form in a combination reaction, they often pack quite a punch, and this introduces us to exothermic reactions. These are simply reactions where heat is released along with the formation of products. See, when certain substances combine, the new bonds they form actually require less energy to maintain than the separate elements did, so all that leftover extra energy has to go somewhere. It blasts outward into the environment as heat. Remember that dazzling hot white flame from the magnesium ribbon earlier? Exactly. It wasn't just a regular combination reaction. It was a highly exothermic combination reaction. And the thing is, exothermic reactions aren't just some abstract concepts locked away in a chemistry lab. They are constantly shaping your everyday life. Burning natural gas on your kitchen stove to boil water? That's methane combining with oxygen, releasing the heat you need to cook your dinner. What about the decomposition of vegetable matter into compost in a garden? As microorganisms break down and recombine those organic materials, heat is released. A healthy compost pile is actually remarkably warm on the inside. But honestly, perhaps the most fascinating exothermic reactions are the ones happening inside of you right now: digestion and respiration. But before we fully dive into our own biology, let's look at a super fascinating historical application of this: whitewashing walls. It is such a brilliant chemical story. Step 1. We take calcium oxide, which is commonly known as quicklime, and we combine it with water. Now, this combination reaction is wildly exothermic. I mean, it releases so much heat that the mixture can actually start to boil. And this forms a single new product, slaked lime. Step 2. You take this slaked lime solution and literally paint it onto your walls. Step 3. Over the next 2 to 3 days, the slaked lime slowly reacts with the carbon dioxide gas that's naturally just hanging out in the air. Step 4. The final result of this slow reaction? It leaves behind this thin, hard, shiny layer of calcium carbonate on the walls. And what's really amazing here is that the chemical formula for this finish, calcium carbonate, is exactly the same chemical formula as solid marble. How cool is that? Which brings us right back around to that incredible exothermic reaction happening inside your own cells. To stay alive, we obviously need energy. We get this by eating food, which gets broken down into simpler substances like glucose. Then, our body does something totally remarkable. It takes that glucose and it combines it with the oxygen we breathe in. And the result of that reaction? Carbon dioxide, water, and crucially, the release of the massive amounts of energy we need to walk, talk, and just live. So, is our own breathing, our very existence, essentially driven by a slow-burning, heat-releasing combination reaction? Absolutely yes. You are a walking, breathing chemistry marvel, constantly combining elements to generate the energy of life. Keep that in mind the next time you take a deep breath, or even just feel the heat of your own body. Thanks for hanging out with us for this explainer, and keep exploring the incredible reactions happening all around you.